Hello everybody. So the purpose of this video is to review some linear algebra concepts that can be helpful for us in our process control course. Okay, so the first thing we should remember from linear algebra is what is a linear equation. So a linear equation is an equation of the form a1 x1 plus a2 x2 plus an xn is equal to some scalar b, and the condition here is that a1, a2, all the way to an are scalar numbers. Also for linear equations, everything is a power of 1. There are no logarithmic, no exponential, no sinusoidal functions. So pretty standard stuff is just the general form of linear equation. Now, when we talk about linear algebra, one of the powerful tools we get to do is to solve systems of linear equations. We all know when we have a couple linear equations, it's usually not too hard to solve. We can use some basic substitution elimination. But when we get into, say 5 linear equations, it's not so easy. So we'd like to develop a more concrete way to solve these. So for example, take the system of linear equations 2x1 plus x2 minus x3 equals 1, x1 plus x2 plus x3 is equal to 6, and negative 3x1 plus 2x2 plus 4x3 equals 13. So say we want to solve the system of equations. Now in linear algebra, we're lazy. We don't like to write a lot of things in long ways, so we often write this in a compact formula. We like to write a matrix with the coefficients here. So in the matrix, we'd have 2, 1, negative 1, 1, 1, 1, negative 3, 2, and 4. So these are our coefficients here in our equation. This would be a 1, this would be a 2. So that's our coefficients. We multiply this by our vector x1, x2, x3, and that is equal to the right side of our equation, which is 1, 6, 13. Now another common way to visualize this, or a common way you might have seen in remember from linear algebra, is that we call this our matrix A. This is our vector x, and this is our vector b, our right side of our equation. So we have the formula ax equals b. Just a quick side note too, another way to represent this is to take x1 times our first column, 2, 1, negative 3, plus x2 times 1, 1, 2, plus x3 times negative 1, 1, 4. These are our columns. And this is equal to our b, which is 1, 6, 13. Also, just to preface, I'm not an artist, so please don't hate on me for this. Okay, so now to solve the system of linear equations, we put in matrix form ax equals b. We want to use something we like to call Gaussian elimination. And now Gaussian elimination is really an algorithm to solve n linear equations. So this is our row operations. In our Gaussian elimination row operations, there's actually 3 allowable operations. So the first one is that you can interchange any 2 rows. The second is that you can multiply any row by a scalar. And the third is that you can add any multiple of one row to another. So now an example of this, here I'll just draw in green, would be the operation taking R1 and you switch it with R2. An example here would be take the row R1 and you multiply that by 3. And an example corresponding to point 3 here would say take R1, our row 1, and we add, let's say 2 copies of row 2. So that's just an example of what this means. So let's do a concrete example. Let's actually just solve our system of equations we had before. So I'm just going to write it out again. So when we solved the system, remember we wanted to solve ax equals b, which means we want to solve for the vector x, which is x1, x2, x3 that makes this true. And to do this, we want to solve the row reduce the matrix here, A augmented with our B. So in this case, we take our A, which is our coefficients, 2, 1, negative 1 for the first row, 1, negative 1. The second row is all 1s. And the third row is negative 3, 2, 4. And we augment this, that's what that vertical line means, augmented matrix, with our B, which is 1, 6, 13. Okay, so now we want to row reduce this into a form that we like to call in linear algebra, we call it row reduced echelon form, which is the form as follows, where you have ones along the main diagonal and zeros everywhere else. And what this tells us is the solution to x1 is some number, x2 is some number, and x3 is some number. So this is our row reduced echelon form. We want to form a staircase of ones here. Everything else is 0. So first things first, the first operation I like to do here is I'll actually write out the operation. I'm going to switch R1 and R2. I'm doing this because R1 has a 1 right here, so it just makes it easier. We get a 1 in the top left. So what we get when we do this is 1, 1, 6. Our R2 comes here now, negative 1, 1. Negative 3, 2, 4, 13. Okay, done our first row operation here. We formed a pivot in the top left. We're going to want to use this leading one here, to make these entries here equal to 0. So what we can do is we can take R2 and we can subtract off 2 times R1. If we can take R3 and we can add 3 times R1. So what this will give us is, well, R1 is going to be the same because we are not operating on R1 here. We're going to take R2 and we subtract off 2 R1, so this will become a 0. This will become a negative 1. This will become a negative 3. And this will become a negative 11. This is a 0. This is going to become a 5. 2 plus 3 times 1. This will become a 7. And this is 13 plus 3 times 6, which is 31. Okay, so that's the next operation. Now, I don't like having negative signs, and we want to create another leading one here. So we've already gotten the first leading one, our REF. So I'm going to take R2 and multiply this by negative 1. And so what we get is, well, first R1 and R3 are going to be the same. Oh, sorry, this is not a 6. This should be a 1. So this is going to be a 1. This is going to be a 6. R3 is still 0, 5, 7, 31. And R2 will just be 0, 1, 3, and 11. Okay, so now we have 2 leading ones. We're going to use this leading one here to create zeros in these entries here. So we're going to take R1 and we're going to subtract off R2, and we're going to take R3 and subtract off 5 times R2. And so R2 is not being operated on, so we're going to write out R2 because it stays as is. Now R1 minus R2, this will stay a 1, this will become a 0, this will become a negative 2, this becomes a negative 5, this is a 0, 5 minus 5 is, 0, 7 minus 5 times, 7 minus 15, this will be negative 8, and this will be 31 minus 55, which is minus 24. Okay, perfect. Now let's take R3 and we're going to multiply times 1 over negative 8. We're basically just dividing by negative 8. So row 1 and row 2 are going to stay the same. This is a negative 5. This is 0, 1, 3, 11. This will be 0, 0, 1, and this will become a 3. Perfect. So now we have another leading one here. And as you guessed, I'm sure we're going to create 0 entries here. So as you can probably already write down yourself by now, we're going to do R2, which has a 3, and we want to make this a 0. So we're going to take R2, and we're going to subtract off 3 times R3. We're also going to take R1, which has a negative 2 here, which we want to make a 0. We're going to add 2 copies of R3. So doing this, remember, we're not operating on R3, so we can just simply write out R3 here because we're not changing it. So now this is 0 still, this is the 1 still, so we're going to do R2 minus 3 R3, so this will become a 0, 3 minus 3, and this is going to be 11 minus 3 times 3, this becomes a 2, this will become a 1, a 0, a 0, and we're going to do negative 5 plus 2 times 3, 2 times 3 plus 3 times 2, which becomes a 1. So this is our RREF form. And so what this tells us is that we have the solution x1 equals to 1, x2 equals to 2, x3 equals to 3. And so this is the solution to our system of equations.